Good evening, everyone, and welcome to the sixth in a series of webinars on CO2 pipelines and infrastructure for CCS. Tonight's webinar is entitled Carbon Capture and Storage, Climate Savior or False Solution. My name is Lan Richard, and I'm a co-director of the Eco-Justice Collaborative in Champaign, Illinois, and a founding member of the Coalition to Stop CO2 Pipelines. With humanity heading deeper into a climate crisis every day, carbon capture and storage, or otherwise known as CCS, has been thrust into the forefront of U.S. climate mitigation policy. CCS, of course, is the process of actively removing carbon dioxide from the atmosphere and/or capturing it from the carbon-emitting industries, then transporting it via pipelines where it will be injected underground with the expectation that it will remain there in perpetuity. Despite CCS's dismal performance record and the legitimate concerns over its long-term safety and exorbitant costs, the US government is now going all in, making tens of billions of dollars, perhaps hundreds of billions of dollars, accessible to oil and gas companies and their affiliates to build out a massive network of specialized pipelines and intended to transport CO2 across country to designated injection sites. The concept of capturing carbon emissions and storing them underground is certainly attractive for those receiving large grants for CCS research and development. Fossil fuel companies love the idea because it prolongs the use of fossil fuels and the profits that come with it. And CCS is also attractive for elected officials who are seeking a politically palatable response to climate change that strikes a balance with the fossil fuel advocates and asks very little from the public. But does the science justify an immediate and all-out commitment to CCS as the primary tool for reducing carbon emissions? Or, at this moment, is there a better use of our climate-fighting resources? Tonight, we're privileged to welcome three experts who will discuss carbon capture and storage technology, why it may not be ready for national implementation, and what alternative pathways to addressing climate change exist that don't rely on costly and unproven technologies. Each of our guests will be speaking for approximately 15 minutes. If you have questions during their presentation, we ask that you type them in using the Q&A button at the bottom of your screen, not the chat, but the Q&A button. We'll try to get as many questions in as we possibly can at the end of our program. So with that, I'd like to invite Mary Sheskrin, board member of SOIL, Save Our Illinois Land, to introduce our first guest.
Hi, my name is Mary Sheskrin, and our first speaker is June Sequeira. June is a visiting scholar at the New School for Social Research. She's a senior research fellow at Boston University's Global Development Policy Center and a senior research associate at the Institute for Innovation and Public Purpose at University College of London. She has a wealth of academic credentials, a daunting list, but before she got involved in that academic work, she was a public policy practitioner and manager with over 30 years of experience at the federal, state, and local levels of government. So she knows how government works. In her scholarly work, recently, she has focused on policy with regard to one particular form of climate change intervention, and that is reducing atmospheric carbon dioxide. And then she initiated and directed a project to investigate the scientific literature on industrial carbon dioxide removal methods From the perspective of public need, the project used a standard of collective biophysical need to gauge the effectiveness of various technologies. The results were published in October 2020 in Biophysical Economics and Sustainability. The findings of that research included the discovery that in the United States, federal and state governments are offering subsidies for carbon dioxide removal methods that emit more CO2 into the air than they remove. This paper was cited by the Intergovernmental Panel on Climate Change itself in its report this year on climate change mitigation. I first heard June Sequeira speak about carbon capture and storage at a dinner, Chicago Area Peace Action dinner in Evanston in 2019, and she got me so riled up about carbon capture and storage that I'm still riled up about it, and it's the reason I'm part of this coalition to stop carbon dioxide pipelines here in Illinois. So take it away, June Sequeira.
Thank you, Mary. Yes, it was great to meet you back then, and that was pre-COVID when we were able to do meetings in person, but I really appreciate the invitation to talk to your group today. Thank you so much for the invitation. So let me try to share my screen here. Okay, my slides are visible. Yes, okay. So what I'm going to talk about today, and I'm going to go pretty fast because I have a lot to cover, is the basics of carbon capture, what it is, how it fails at reducing atmospheric CO2. What are the premises of carbon capture? Well, one is that we can catch our emissions and negate them by storing them, something labeled net zero. Another premise is that these technologies will reduce the CO2 that's in the air, and they'll do it fast enough and permanently. Another premise is that captured carbon can either be utilized or safely buried underground, and all of these are actually false or dangerously misleading. So what I'm going to cover tonight is how carbon capture does not solve or even address the fundamental problem that we have, but still taxpayers are subsidizing it many times, most of the time without their knowledge. And secondly, the carbon capture process poses harms to people and places, and I'll go into what those are. You've probably heard these terms: carbon capture, carbon technology, net zero, carbon management, carbon recycling. So these sound good, some sound great, some sound like they're professional, or they sound, carbon recycling sounds fabulous. Well, the situation that we're in is that promoters of carbon capture have crafted this vocabulary, and they have thus controlled the conversation. So these are means, but to what end? To what end do these means are they supposed to go? What I argue is that we need to change the terms of the debate. The conversation right now has been caged in the vocabulary crafted by its promoters. And I'm going to just read this slide because I'm going to leave it in the slide deck as is in case anybody wants it later on. So what I'm arguing is that we must turn the conversation around, talk first about the need, the problem that must be fixed, which is what I did in my research, and only then talk about ways to solve it. So I want to start by talking about the problem, and this is not what's been done by those who are promoting carbon capture. And then we need to talk about the harms to people and places. And I argue this is the context in which to have the conversation about carbon capture. Well, first of all, what's the problem? The problem that needs to be solved is the concentration of CO2 in the atmosphere. So for 6,000 years of human civilization, the level was at 280 parts per million, ppm parts per million, until the fossil fuel revolution, also called the Industrial Revolution, which was about the mid 1700s. And now we are at 420 parts per million. This is a line graph of what I've just said, the same numbers about the level of CO2 in the atmosphere. And the point is, an important point is that the carbon cycle has kept the balance, did keep the balance for thousands of years until we started emitting and using fossil fuels. And this is the carbon cycle. I'm not going to go into it, but most of you are very well aware of this. But this is what's kept the CO2 in balance for millennia. But what we have now, we've had an accumulation of human-caused emissions in the last 250 years that gets us to the level now. The problem is that capturing emissions does not deal with the existing human-caused buildup of CO2. And even if mechanical carbon capture could achieve net zero, we'd stay at 420 parts per million where we are for a long time, causing planetary temperatures to continue to rise. And some carbon capture methods actually increase the level of CO2 in the atmosphere, as my research revealed. So where are we now in terms of emissions, concentration, and carbon capture? This is a very busy slide, but I want to, I put it all in one place. So I want to start first with the left-hand side, the human-caused emissions per year. And the causes, of course, are fossil fuel combustion and ecosystem destruction. So where we are right now is we're emitting globally 39 gigatons, 39 billions of tons of CO2 per year. And of that, the United States emissions are 5 gigatons, 5 billion tons. Moving to the right-hand side of the slide, is carbon capture reducing the amount of CO2 in the atmosphere? The answer is no. CO2 removed from the atmosphere now by carbon capture is basically nothing. I'll go into this in detail in a minute. Carbon capture removes nothing now. In the United States, the amount of carbon that's captured and stored is 0.02, 200ths of a gigaton per year, but that's not removing anything from the atmosphere, zero being removed by our methods now. Globally, the amount of CO2 being captured and removed from the atmosphere is 4 millionths of a gigaton. So someone used the term recently about the futility of carbon capture, and I thought that was a good term, so I picked it up. The futility of trying to address the climate crisis in this way and the harms it poses to people and places, which I'll go into in detail. So we are removing, as of now, nothing from the atmosphere. But scientists say we'd need to get to 6 to 10 gigatons, billions of tons of removal from the atmosphere annually by 2050. That's from zero now to 6 billion by 2050. That's an awful, remarkable acceleration. McKinsey and Company, which has now entered the carbon capture scene, has pointed out the quote there that I'll just read. The world's first large-scale DAC plant with 1 million tons of CO2 capacity in the United States will not be operational until the mid-2020s. This is the plant that's being built by Occidental Petroleum in Texas. To reach the IPCC's 6 gigatons target would mean building 2 million tons CO2 plants per week between now and 2050, 2 plants per week at this level. And Occidental has been saying that they're going to open this plant for the past, I think, 3 years, and they haven't even done groundbreaking yet. And actually, McKinsey's arithmetic is wrong. We would actually take 5 million ton plants to open per week through 2050 to get to the 6 gigatons minimum. And that assumes, of course, that every one of those plants comes online and starts working perfectly and at capacity from day one. So this seems like a good illustration of the futility. Also, another issue is energy use. To capture only 1 gigaton of CO2 would consume almost as much energy as the amount of electricity generated in the US in 2017. And of course, to remove 6 gigatons would take 6 times that amount. These are data from the last IPCC report that came out in work group that came out in April this year. I just want to focus on the numbers in the little table there. The DACCS is direct air capture that's pulling the CO2 from the air with storage. The IPCC's data, if you look into the report itself, not the headlines that get printed by the media, you'll see that the IPCC is saying that that we're going to be at only 0 gigatons by 2030 with using direct air capture, these mechanical means. And by 2050, we'll be at 2/100ths of a gigaton. And by 2100, we'll only be at 1 gigaton, is what the IPCC is saying. And, although this is not what's reported in the headlines. So what I want to do right now is to get into the details of what carbon capture and storage is, the process. It's a multi-stage mechanical, chemical, industrial process, and it works in 2 ways. One is to capture emissions coming from smokestacks, and the other is to pull the accumulated CO2 out of the air. And the process I'm talking about here, I just want to underscore, is mechanical chemical carbon capture, usually called technological, not biological sequestration. That's a whole other topic. So the process is 3-part, as Lance said: capture the CO2, transport the CO2 somewhere, and do something with it. So the capture process, there's 2 types of carbon capture. One is called point source capture in the literature. It's called CCS and CCUS colloquially, and that's meaning trap the emissions coming out of smokestacks. The other method is to pull the CO2 out of the air, which is called direct air capture. And the important thing I want to stress, and this slide is meant to show, is that these are industrial processes. Industrial machinery traps the flue gases coming out of the smokestacks or sucks the air in the ambient air. And chemicals are used to separate out the CO2. This is a list of some of the chemicals that are used. They'd have to be produced by the millions of tons per year and transported per year in order to get to start to reach those levels that the scientists say we need to leave. And all are toxic and pose dangers to communities. This is a list of the current US carbon capture sites. One thinks that there must be dozens and dozens of them, or hundreds, but no, there's only 12. At least there was as of these data, which are from 2021, and I don't think there's been too many more, maybe 1 or 2. They're all enabled by taxpayer subsidies. And all of these projects, none of them is at a power plant. None of them is direct air capture. They're all source capture. And I really want to stress, we'll be hearing more about carbon capture at power plants a little bit later, but I want to stress that every single carbon capture project at a power plant in the United States has failed, and it's failed using government money. This is a list of them that have been tried, and every one has failed. There's only one carbon capture operation at a power plant on the planet right now, and that's the facility in Canada, which when it causes the price of electricity to double. So carbon capture fails to reduce the level of CO2 in the atmosphere. And it does so because source capture removes nothing, and DAC in the US will be powered mostly by fossil fuel. And this is just a chart that digs into that information. And so carbon capture from smokestacks can actually increase the amount of CO2 in the atmosphere when we're talking about CCS at coal-fired power plants with enhanced oil recovery. Studies have shown that it's 3.4 to 4.7 times as much CO2 as it removes. And DAC, pulling the carbon dioxide out of the air, this is that major plant that's planned by Occidental Petroleum. It'll be powered mainly by fossil fuel. Its business plan relies almost entirely, very largely on government subsidies, which they've been very upfront about. The carbon that's captured will be used for new oil extraction. It aims to capture 1 million tons per year. DAC, when it's fossil fuel powered, emits 1.5 to 3 times as much much CO2 as it captures. There's another project being discussed, Project Bison, that's also, I believe, from what I can tell, are going to be powered by fossil fuel. The largest DAC plant in operation right now is operated by a company called Climeworks. in Iceland. And as one scientist said, in a year, it'll capture just 3 seconds worth of humanity's annual emissions. So continuing with the process, again, the mechanical capture process, once you've captured it, you have to do something with it, transport it to a location to use it or to bury it. So what are the choices of what to do with it once you've captured it? You can inject it underground for storage, you can sell it as chemical feedstock, or you can sell it for oil extraction. And in the United States right now, of those 12 projects, 95% of the captured CO2 is used for EOR. And what's EOR is one report recently that recently came out said it's injecting CO2 to emit CO2. The process injects CO2, carbon dioxide, into existing oil wells to flush out remaining hard to pump oil. So moving on to the harms. The harms that many of you are more familiar with than I am, but the problem is global and the perils are local. We have community wealth depletion, loss of control, value depletion for houses and farms, risk bearing, like things like water contamination. The long-term liability is legally being put upon the communities and the states for leakage and blowouts. There's a lack of local control and eminent domain, which I'm sure some of you have had experience with, seizures of land for CO2 pipelines and storage. I also want to point out something that isn't talked about much. This is in a report by the National Academies of Sciences about CO2 depletion zones, which means regions of local CO2 depletion that would have adverse impacts on crop efficiency and the overall health of local habitats. So what about pipelines and storage? First of all, before you can put CO2 into a pipeline, you have to compress it. This is a picture of the ADM Decatur, Illinois ethanol facility and their compression operation to get the CO2 into a pipeline to compress it for injection. These are compressor booster stations that would need to be built along the pipelines in many cases. This is a picture of the planned pipelines in the 6 Midwestern states, which I'm sure most of you have seen. So I won't dwell on this. And this is a picture of the pipelines that are projected to be needed for transporting less than a gigaton of CO2 annually. This is a report by Princeton that said 66,000 miles of pipelines. This is about a pipeline rupture. There are hardly any pipelines right now. There's about 5,000 miles of pipelines, CO2. And this is a rupture that occurred in Mississippi in 2020. And the enormous cloud of CO2 that came out of this pipeline rupture spread for miles around and knocked people unconscious and almost killed several people. What about storage? This is a diagram from a handbook by the US Department of Energy about the failure modes, potential failure modes and effects when you inject CO2 into saline storage. And indeed, Navigator, the pipeline company in your area, is planning to use to inject the CO2 into saline formation. And as a recent report by IEEFA recently said, it is impossible to guarantee that stored CO2 will stay underground. And this diagram certainly supports that. The premise is that underground storage is safe. This is a list of just some of the leakage that has occurred in the blowouts that have occurred from carbon capture from CO2 underground storage so far, and there hasn't been all that much so far. This is a slide about the costs, and I just want to focus on the little rectangle down at the bottom there. For pulling CO2 out of the air using direct air capture, and to get to that level of 6 to 10 gigatons per year that scientists say we'll need, would take $3.6 to $6 trillion per year, and not counting the cost for transport, injection, and storage. That's how much it would cost to get to those levels the scientists are talking about. And bringing it more locally, this is carbon capture at power plants, the effect on the price of electricity. It can double or even triple. And that's because the operation of CCS at power plants cannibalizes energy. It raises operational costs, and the result of that is raised costs to customers. That plant in Canada The cost of electricity there went up from $60 per megawatt hour to $120 per megawatt hour. So to summarize here quickly, what we have, I think, are public subsidies that are dressed up to look like a market solution. And without taxpayer subsidies, private companies in the US could not be making money on carbon capture and storage because it's not a market. The term market is used, it's thrown around a lot, but what you're doing is really throwing away the product, burying it underground. And this is not a market transaction, it's waste disposal at US taxpayers' expense. Utilization is unrealistic because, as many scientists have pointed out, there's no private market for the billions of tons of gigatons of CO2 that would have to be utilized annually to have any climate effective impact. And to be sure, advocates say that it'll get cheaper and more effective, but even if it does get cheaper and more effective, taxpayers will have to subsidize it perpetually because there's no other customer but government when a business is burying its product underground. So CO2, as Klaus Lackner said, the grandfather of DAC, carbon removal is waste disposal. And as someone else said, what we're building here is a publicly financed sewer system for the fossil fuel industry. Quickly, what could work? Back to the data from the IPCC, focusing now on the green font in the chart there. The IPCC data show that biological methods can actually, we're at about 1 gigaton now, and we'll be at almost 1 gigaton by 2030. By 2050, we'll be at almost 3 gigatons per year net removal, and by 2100, 4 gigatons per year net removal. Compared to DAC, there's a stark difference. And how would that be done? The biological methods, by enhancing replanting forests, farmlands, grasslands, and wetlands. So and I just completed some more research that showed that basically supports or is in line with these data that I can't go into now because I don't have time. But based on my research with about 6 colleagues and the IPCC data, I would say that the subsidies for mechanical carbon capture should instead be used to pay communities, farmers, indigenous groups, and public agencies to adopt and expand regenerative agricultural practices, to plant trees in urban and rural communities, to restore forests, grasslands, and wetlands. Thank you very much.
Thank you, June, for all of the work and for bringing that to us. Our next speaker tonight is Dr. Albert Carvallis. He's received his PhD in engineering from Penn State University, and he practiced mechanical engineering and held management positions in industrial research, product design, and failure analysis. He has served on both the American National and the International Standards Committees and the National Bureau of Standards Committee on Failure Prevention. He's also practiced academic work where he's taught seminars on safety and ethics in engineering design and graduate level courses on fatigue, fracture mechanics, and vibration at Northern Illinois. He's also earned many distinguished honors. He's been elected to the status of Fellow in the American Society of Engineering International and to the Sigma Psi National Honorary Research Society. Our next presenter, Dr. Carvallis.
All right, this is the Prairie State Generating Company. And I'll give you my engineering view of what I think is going to happen. And from my perspective, the conclusion is on the bottom. It says an experiment. This is not a project, in my opinion. This is an experiment that's likely to fail on many levels. Now, June talked about taxpayer dollars. Since 1990, nearly 700 million taxpayer dollars has been spent on so-called clean coal projects. In the last year, literally billions more have become available. The US Department of Energy is painting a very green picture publicly on clean coal projects. However, that's really not that accurate. So what I have here, we've already gotten an introduction. The view on the left is an idealized view that's presented to a lot of the public and to some of our Congress people. clean coal coming to a power plant that has got no emissions, simply generates electricity on its property. Carbon dioxide is captured and stored. Now, the next to the right, on the right-hand side, I have a slide that is taken from a brochure of MHI. Now, MHI is one of the team players that is designing the carbon capture facility, has designed the carbon capture facility at Prairie State Power. Now, they reveal very openly that the goal of carbon capture is for enhanced oil recovery. And as June said, you can see in the drawing, the thermal plant goes to a capture plant, and that's injected into the reservoir, and then that's gently shipped over to a place that has trees and buildings. Again, very highly greenwashed. So the historical purpose of the CO2 capture from fossil fuel power plants has been both to keep burning more coal and to pump more oil from depleted oil wells. Okay, we'll go to the next slide. All right, so here's the project. The $17 million project just recently completed was sponsored by the Department of Energy. And not surprisingly, the department is called the Office of Fossil Energy and Carbon Management. The project was run through the University of Illinois Prairie Research Institute. This FEED project, FEED, Front-End Engineering Design, completed the engineering design capable, allegedly, of capturing 95% of the CO2 from Unit 2 at a cost of around $45 a ton. If completed, this would be the world's largest so-called clean coal carbon capture facility. The stated destination for this captured CO2 has been injection into deep rock formations. However, there is no permitted approved site on the property to receive 13 million tons of compressed CO2 per year. Certainly not on the property. So therefore, there is no estimates provided by this FEED study on what it will cost to compress the gas and to transport it, who knows where. Now, once operational, the capture equipment, if it worked, would cost the taxpayer in carbon credits about $500 million per year. The design of this carbon capture creates a number of environmental issues. Avoidance and navigation around these issues is accomplished by creating a brand new business entity to own the equipment, as illustrated in the next slide. So this is kind of important because a lot of danger lies in this. On the left, this is a greatly simplified diagram showing this feature of separation. There's only really one smokestack at Prairie State Power, but I show two. And that's to emphasize the fact that after billions will be spent on reducing CO2 emissions from unit number 2, unit number 1 will still be emitting all of its 7 million tons of CO2 per year and its share of 2.5 million tons of methane. The separate business entity on the right-hand side would own and control the equipment. They would pay Prairie State for Unit 2 for dirty gases, extract as much CO2 as they possibly could, and return whatever is left to the smokestack. So there's not a whole lot of gain done, even if it worked well. And of course, the natural question to arise when you look at this operation is, if this is going to be the largest clean coal project in the world, what has been the experience elsewhere with smaller clean coal projects? Let's take a look. Okay, failure. So you can see that the previous smaller clean coal capture product is really in trouble. It doesn't look like there's a lot of success to build on. So let's take a look at this. We see this is called Petronova. Let's take a look at Petronova. Petronova, carbon capture facility. All right, it's the only US coal-fired plant that had installed CO2 capture operation. The target was for 90% capture. It started in December 30th of 2016, and it closed in 2020. Now, not only is it a quarter the size of the plant in downstate Illinois, the unit 2 being 816 megawatts, not only is it a quarter the size, but they only siphoned off part of the gases from Petronova to treat it. During its, quote, lifetime, unquote, Petronova captured only 7% of the entire plant's CO2. And what's interesting is the EOR, of course, it was designed right from the start to send its carbon dioxide to make more oil. On its best days, it was able to build 5,000 barrels of oil in one day. And what's interesting is that the Department of Energy, this Office of Fossil Fuel, touted it. They were extremely proud of how wonderful it was that their carbon capture facility was able to add 5,000 barrels of oil in one day to our planet. So here's the question. If you failed to achieve a 90% capture level on a medium-sized coal plant, why on earth would you expect to succeed at a 95% capture level on a plant nearly 4 times larger? The design team, I don't know if I mentioned it, but it's the same design team for Petronova, basically, as in Prairie State. The design team's answer is lessons learned, quote unquote. I, on the other hand, call it overreach or hubris. Now, there's another factor that the Petronova team implies will make Prairie State a success: a new miracle solvent to extract the carbon dioxide from combustion gas. It is called KS21. So here's this infomercial in Forbes magazine, KS21, a new improved super solvent. And perhaps, and maybe, it does capture 99.8 of the CO2 emissions someday, somewhere. But this testing that they're reporting, this success, was done on a gas turbine. That's the same as the engine on the airplane, was done on a gas turbine engine in Norway over a 3.5-month period. It was not done on a large coal plant. So the KS21 marketing people reporting getting very good results. That is, I believe, a little bit overreach on marketing. So moving on to the next slide. This is a very interesting thing I discovered when I was looking at the project to design the carbon capture facility. I don't want to spend much time on this, but this is interesting. The steering committee for the Prairie State Design Project was not only chaired by the CEO of Prairie State, that is the coal plant, but also included a lobbyist, a lawyer, investor, and a PR person. Now, I can't think of a single legitimate reason for this type of steering committee structure. The only thing that might possibly explain such an unusual arrangement is if there is a political agenda that needs to be enforced. Agenda-driven oversight is typically not conducive to best technical results, and accordingly is another potential failure predictor in my experience. Time allows me to list only a few of the main failure indicia that I found in this project. Remember, I was asked to take a look at this as a project per se. What's going to happen? Is this going to work or not? These indicia that we talked about, while not fatal in and of themselves, taken together, point to a reasonable expectation of failure. So this is not a project that's building on other things that the federal government is sponsoring. This is an experiment. And here, let's go through the indicia, just some of them. Overreach, the only US attempt, quarter size. Petronova, it failed. Supervision, the steering committee overstaffed with political types. That's a failure indicia. New and improved super solvent. KS-21 has not been proven in large coal-fired plants. Separate operations. Now, I talked about how the separate operation, they buy and treat and send it out. The principal reason is for to avoid environmental regulations and navigate around them. And number two, to get the money more handily from the government. However, from an engineering perspective, you have two vehicles, two drivers with different motivations. That is a recipe for disaster. Destination, there's no campus site for storage. So that suggests that there's going to be a pipeline. And they've avoided all discussions about this project and the release to the public, such as in published papers, etc. They have avoided this issue that it's going to somehow be connected to a pipeline somewhere. They're just avoiding it. Investor interest, there's none apparent. There's a parallel, similar type of project that's being touted in New Mexico or attempting to get off the ground. And they were much more open and frank about the fact that as June said, there's no market forces here. You're going to need not only a carbon credit handout, but you're going to need you're going to need to have loans made. You're going to have to guarantee the loans. You're going to have liability waiver, et cetera. And the environment, as June said, there's the idea if to call this project successful at worst, at best, I should say, you have to have no increased environmental damage. And that's not possible with the chemicals that they will be using. All right, clean coal project drivers. I think June covered some of this, but interestingly, CEJA, the Illinois, has a requirement in their own law which says that the state should encourage the use of advanced clean technologies that capture and sequester carbon dioxide. Department of Energy, as I said, almost $700 million in clean coal projects. The Infrastructure Jobs Act, $12 billion administered to DOE, is dedicated to carbon capture and sequester technology. Emphasis is on storage and sequester from coal burning plants. The recent IRA Act goes even further. Not only is it released additional monies for these quote unquote demonstration projects, but it's reduced the minimum annual capture from 500,000 tons to 18,750. So they are on a religious mission practically to spread this technology. And again, as we saw in an earlier slide, the purpose of this is to keep the coal industry alive. Plus we have Oklahoma, Texas, West Virginia, and Wyoming, the legislatures, the legislators from these states. The most surprising thing I discovered in doing the research when I came upon the finding that one of the biggest champions of carbon capture is Senator Hofi of Oklahoma. And you couldn't find anybody that was more conservative. And that's when I discovered that what is the long-term objective of this? All right, there's several open issues that really concern me. As I implied in the previous slide, there are immense pressures to make this plant adopt and get this carbon capture equipment going and to become, quote unquote, the world's largest carbon capture facility. I believe it's going to happen because of those the financial pressure. There's too much money chasing this, and there's too much political power chasing it. So the thing that really concerns me also is the fact that, besides the waste of money, is that unless the state legislature in Illinois expressly prohibits the use of captured CO2 for use in EOR, enhanced oil extraction, for an investor-owned carbon capture facility. Let me back up a little bit. As I said, Prairie State is owned by, I didn't say, Prairie State Power is owned by a number of municipalities around Illinois, West Virginia, Kentucky, and I think Indiana. So in a way, it's not really a private capitalist, investor. This facility would be. It'd be entirely investor-owned and operated. So for an investor-owned carbon capture facility, even if a pipeline is set up, even if EOR will always be an option if the money isn't flowing just so. What that means is carbon is extracted from the ground in Marissa, Illinois. It's crushed, it's fired. The carbon dioxide is extracted from the flue gas under best conditions, is sent to an oil field where it's released back into the atmosphere. And the carbon goes from being coal, being stored as coal, goes back into the air. The only people that have made money are the coal plant runners. Now, I believe that from all of my background, this mechanically will fail, and failure always results in unexpected consequences, and that results in litigation. So who pays that? So, summary. Financial plus political forces means carbon capture at Prairie State will happen in around 2027. Grants, loan guarantees, liability waivers. It would take an enormous effort to stop that. Overreach, that means what they're trying to do technically will result in the wheels coming off. Consistent 95% target capture will not happen. If I were to guess, I would say closer to 60, 70% at best. The pipeline to enhanced oil extraction, it'll become a rescue option for owners unless it's prohibited. And then there's the flexible capture criteria. And I've already heard backroom mumblings about this. There are standards that people try to impose. If you're going to have it, you have to capture 90% of the carbon dioxide, and so on and so forth. And same thing with the state of Illinois. You have to reduce your carbon dioxide by so many percentage by this and such a year. Once the failures start propagating, what will happen is that the criteria will become very flexible. It's going to be like we call in engineering the archery technique. First you shoot the arrow, then you paint the target. So this, I feel, is going to happen. What's acceptable, maybe 95 to someone, is going to be ratcheted down to whatever it is that they're able to squeeze out of it. Meanwhile, Prairie State will continue to burn coal, make coal actually emit CO2, methane, and so on. And I'd like to leave visual reminders for people. Carbon capture in coal plants. You can always try to drive a screw with a hammer to join two pieces of wood. It might work, but believe me, you won't like the result. And those of you that love data, here's the tax money. Those of you that are engineering oriented, here's a whole lot of technical stuff. And those of you that are environmentally oriented, this is the enormous amount of pollutants that plant produces. Thank you.
Now it's my privilege to introduce our final speaker, Dr. Mark Jacobson. Dr. Jacobson is a professor of civil and environmental engineering and director of atmosphere and energy program at Stanford University. His career is focused on better understanding air pollution and global warming problems and developing large-scale clean renewable energy solutions. Through his research, he's developed and applied three-dimensional atmosphere, biosphere, ocean computer models to simulate air pollution, weather, climate, and renewable energy, and has developed roadmaps to transition to 100% clean renewable energy for all. Dr. Jacobson has published over 175 peer-reviewed papers on his research and is sought after as a speaker at conferences, workshops, and lectures around the world. Has previously authored 5 books on atmospheric modeling and global warming and renewable energy, and has a 6th book coming out early next year entitled No Miracles Needed: How Today's Technology Can Save Our Climate and Clean Our Air. By the way, you can pre-order the book at Cambridge University Press or on Amazon. So now I'd like to turn the evening over to Mark Jacobson.
All right. Thank you very much for that kind introduction. I'm just going to share my screen here 1 second. I assume everybody can see this. So I'm going to talk about carbon capture, direct air capture, and blue hydrogen, which involves carbon capture as well. And like the previous speakers, I'm going to emphasize the main issues, but I'll add some additional issues that haven't really been covered. Start with carbon capture, and I'll actually give you data from the Petronova plant that was mentioned in the last talk. So I actually analyzed the data and looked at it from kind of probably a different point of view than most people had looked at it. Well, anybody had looked at it from before. So because I'm looking at it from an air pollution and a climate and an energy security point of view, but also looking at the cost as well. And I'll start here with the emissions associated with the carbon-related emissions. So this table shows over a 20-year time frame or a 100-year time frame the carbon dioxide equivalent emissions from the Petronova coal plant in Texas before and after carbon capture was added. So before carbon capture, we had 450 over a 20-year time frame, and this is the relevant time frame. So I'm going to focus on 20 years because that's the time frame in which significant climate damage may become irreversible, but that's the time frame that we're actually, the climate damage we're seeing is relevant to, not over 100 years. So over a 20-year time frame, there are 450 kilograms of CO2 per megawatt hour of electricity generated from the coal plant due to just the upstream mining of the coal. And then from the coal stack at Petronova is 930 kilograms per megawatt hour. So we're talking, total of about 1,380 kilograms per megawatt hour. At the carbon capture equipment that was added, which was cost $1 billion, so it was basically a tax on the ratepayers, and most of the ratepayers are the ones who pay the highest fraction of their incomes toward electricity or low income. So this is really a tax on low income people. But the carbon capture equipment captured 55% of the stack emissions, or 516 kilograms of CO2 per megawatt hour in the first year. And however, they had to build a natural gas plant just to run the carbon capture equipment for this coal plant. So this is really the crazy part of it. They literally built a natural gas plant for running the carbon capture equipment. And that natural gas plant, the mining and combustion of the gas emitted 367 kilograms per megawatt hour. So they captured 516, but they emitted 367. So the difference is 149. You divide the 149 by the sum of the upstream plus the stack emissions, it's a 10.8% capture rate. And even if you use the 100-year lifetime, it's still a 20% capture rate, not 90% or 95% or anything close to that. And so this is before you even count for what happened to the CO2 after it was captured. Well, of the CO2 that was captured, it was sent to a nearby oil field by pipeline for enhanced oil recovery, just like 75% of all CO2 that is captured today. It's used for enhanced oil recovery. And immediately 40% of that CO2 that's captured goes right back to the air. So we're really talking about, around a little over 6% capture rate, not even a 10.8% capture rate. And who knows what happens to the rest of it? There's no proof it actually stays in the ground. But we do know that there's more oil that comes out, and that oil is burned and creating more pollution. So there's really, in terms of CO2, there's no benefit. But what's worse is you have all this additional air pollution that results. There's no air pollution reduction due to the carbon capture equipment from the coal plant. In fact, now you have a natural gas plant that's polluting even more than without the natural gas plant, and you have the upstream mining pollution from the natural gas plant. So you actually have on the order of 30 to 50% more air pollution from this whole operation than you did before. So you killed more people, in addition to paying a higher electricity rates and hardly reducing any carbon, and certainly not reducing the mining of any coal. In fact, as I mentioned, you have more mining going on, so you have more mining equipment, etc. Okay, so let's look at this from another angle. So on the left curve shows the CO2 emissions. It shows the same numbers. The very left bar, the same numbers of the coal plant without carbon capture. The blue is the CO2 emissions from it's non-methane CO2 emissions from the upstream mining of the coal. The orange is the methane equivalent CO2 emissions from the mining of the coal, and the red is the coal CO2 emissions. So you have only close to 1,400 kilograms of CO2 per megawatt hour. The second bar is this case I just identified, where you then use carbon capture equipment and you run that carbon capture equipment with natural gas. And so the yellow is now the natural gas combustion emissions. The green is the upstream methane emissions from the natural gas. And the purple is the upstream non-methane emissions from the natural gas. Now, the third case is, well, what if people say, well, let's use wind energy or solar energy to run the carbon capture equipment? Okay, well, that does reduce the CO2 emissions compared with natural gas. However, let's say you actually take that wind energy and you replace the coal plant itself instead of running the carbon capture equipment. Why not? Why would you take wind energy to run carbon capture equipment and not take the same wind energy and just replace the coal plant? Because if you use that exact same amount of wind energy, you can get greater CO2 reductions replacing the coal plant or portion of the coal plant itself. But in fact, when you use wind to replace coal, you also eliminate the air pollution, you eliminate the upstream mining of the coal, and you eliminate the coal infrastructure. So that's apparent on the right, which is the social cost of these four different options. The social cost is the energy cost plus the health cost plus the climate cost. So the blue on the right is the light blue is the energy cost. And so you can see the energy cost goes up when you add carbon capture equipment, which are the cases 2 and 3, because you need to pay for the carbon capture equipment. But the energy cost goes down if you take wind and replace coal, and because you're paying for wind energy instead of coal energy, but you end up needing fewer because of the lower cost of wind right now, the energy cost goes down. Now, the brown is the air pollution cost. And so without doing anything, that you can see the brown from the coal, you increase that air pollution cost with the second case. The brown area goes up because you need 25% more energy, or 30% more energy. And they have a natural gas plant to do that, and the air pollution from the natural gas causes more health problems. So that's why there's more brown in the second case. In the third case, since you're using wind, you don't increase the brown, but you don't decrease it either. And in the wind-only case, you decrease the brown because you're reducing the emissions from the coal-fired power plant, so you reduce air pollution emissions. And finally, the black is the CO2 equivalent emissions, the cost of that, the climate social cost of carbon. And you can see with CCU, in the two CCU cases, you do reduce that, but you reduce it more in the wind only case. So you look at the overall effect, the best case by far is just using renewable energy to replace coal, not to use renewable energy to run carbon capture equipment, or to use natural gas to run carbon capture equipment. So let's just summarize the carbon capture and storage use case. Using natural gas to run coal reduces carbon dioxide emissions only 11.8 to 20% over 20 to 100 years. And that's before you even account for what happens to the CO2, while increasing air pollution and mining by at least 25% and incurring a carbon capture equipment cost. Using wind to run coal, carbon capture reduces CO2 only 34 to 44%. This is in the Petronova case, while reducing air pollution and mining 0% and incurring equipment costs. Using the same wind to replace coal itself reduces CO2 emissions, air pollution emissions, and mining by almost 50%, while incurring no carbon capture equipment costs. So there's a clear choice here of what to do. If you want to eliminate air pollution, global warming emissions, and eliminate the fossil infrastructure, you have to replace the coal, not to keep it in play and just try to cover up the problem with carbon capture equipment, which just doesn't do anything. This is really a scam technology that's not helping whatsoever in solving the climate problems. It increases air pollution, and it increases fuel mining, and it increases fuel infrastructure. So why not blue or gray hydrogen? Well, what is blue or gray hydrogen? First of all, gray hydrogen is hydrogen produced from natural gas. Blue hydrogen is hydrogen produced from natural gas with carbon capture equipment. Well, just to preface this, we think you should only use green hydrogen, not blue or gray hydrogen, which both are with natural gas. Only green hydrogen, and only for certain applications. That's long distance vehicles, steel and ammonia manufacturing, and maybe electricity and heat in remote microgrids, but not stationary electricity storage. Batteries are much better, not for heating buildings. Electric heat pumps run on wind and solar are 4 times more efficient, and not for passenger vehicles, because battery electric vehicles are 3 times as more efficient than hydrogen fuel cell passenger vehicles. That does shift when you get to long distance transport. That's why hydrogen is useful for long distance transport. Okay, so what about, well, just to give you an idea, like people are promoting, like right now, like 96% of all hydrogen produced is from natural gas or gray hydrogen. And we want to shift to green hydrogen. But the fossil fuel industry is saying, well, let's just make gray hydrogen blue by adding carbon capture equipment. Well, this really doesn't do much at all. And in fact, it's even worse with blue hydrogen, which uses carbon capture. It even produces more CO2 emissions than just burning natural gas for heat. And I'll show you how. So first of all, the assumptions here, we're using steam methane reforming. We can do the same thing with autothermal reforming, which is another method with natural gas to produce hydrogen, but the results are similar, even worse. Assuming a leakage rate of 3.5%, upstream leakage rate of methane from natural gas mining, transport, and use. And it's actually not a leakage rate, it's really an emission rate, because a lot of these emissions are forced emissions or intended emissions. But just to put that in perspective, the largest gas fields in the world are in Turkmenistan, and their average leak rate just from the fields are 4.1%. There are some overpasses in New Mexico a few months ago. The leakage rate in New Mexico is about 9 to 10%. So we think 3.5% is very conservative here. You can find some low values in the order of 2% or 1.5% in some places, but there's so many places that the leakage rates and the emission rates are very high. So average of 3.5 is pretty reasonable. Carbon capture, when you have methane for producing hydrogen, when you're using natural gas to produce hydrogen, there's actually 2 sources of carbon dioxide that you need to have capture equipment for, not one. One is for the energy to run the steam methane reforming equipment, where if you're burning the natural gas for energy, you need to capture the CO2 there. And then also methane is used as a feedstock to produce the the hydrogen. And so there's actually two sets of carbon capture equipment needed. One, the energy portion, we assumed 85% capture rate, which is pretty generous, considering that this is for pure stream. This is for a pure stream, considering that the only plant that actually does this in the world, the actual capture rate is 78.8%, which is the low value here. We're just assuming, but to be generous, that it can go up to 90% just to see what happens. For the flue gas, which is like for energy, we assume 65% capture rate. Well, that's higher than that Petronova amount, which was 55%. The Gorgon project in Australia, which is the largest natural gas, well, which is the largest carbon capture project in the world, the capture rate over 6 years is 25% now, or sorry, 24%. And then the carbon capture plant in Canada, that's on the order of 55 to 65% as well. And that's over 5 or 6 years now. So, using an average, 65% is probably generous, as illustrated by some of the other data shown in today's talks. But, we also did sensitivities at higher and lower rates. We also assumed a 20-year global warming potential for the reasons I discussed before. And by the way, this is a project with Dr. Bob Howarth from Cornell University. He was the lead author on this. And we published this paper a couple of years ago, got a lot of feedback. But this particular graph shows the grams of carbon dioxide equivalent emissions per megajoule of energy. So gray hydrogen is on the left. You can see there's two colors. The CO2, direct CO2 is yellow, and then the CO2 equivalent is red for methane. And so gray hydrogen has the highest. Then blue hydrogen, you have a slight reduction by capturing some of the carbon. But you can see that just using natural gas for direct heat results in less emissions than using natural gas to produce hydrogen and then capture the CO2. And there's still a huge amount of emissions associated with this blue hydrogen. The best way is, again, with green hydrogen, where there are zero emissions. And it's so simple because green hydrogen, all you need is a photovoltaic, for example, which is an electricity source, and an electrolyzer to produce the hydrogen. With blue hydrogen, you need to dig holes for the natural gas, to mine the natural gas. You need pipelines to transport the natural gas to a refining facility where the natural gas is purified, and then more pipelines to send the natural gas from the refining facility to the steam methane reforming facility. Then you need steam and methane reforming equipment. Then you need two sets of carbon capture equipment. Then you need CO2 pipelines to send it somewhere. And so there's this huge amount of infrastructure. Then you need a place to put the CO2. If it's going underground, you need to make sure there are no leaks. As I mentioned, 75% of CO2 that is captured is used for enhanced oil recovery. So there, 40% of the CO2 goes right back to the air. So this is just really ridiculous. Another excuse to keep the fossil fuel industry alive. And it really has no benefit whatsoever for climate, for air pollution, because in fact, again, in this case with blue hydrogen, you have more air pollution because you need more natural gas you need more energy to run that carbon capture equipment than without the carbon capture equipment. Where's that energy coming from? Well, they're drilling more holes for natural gas. In the US, there are 50,000 new oil and gas wells drilled every year. There are 1.3 million active ones and 3.2 million abandoned ones. The fossil fuel industry takes 1.3% of all US land area, and that's growing every year due to all these mining and pipelines and everything else. And so we're going to cover a much higher portion of the US. If we transition entirely to wind, water, and solar, we need less than 1% of the entire US land area, not more, like the fossil fuel industry needs. Okay, lastly, what about direct air capture? That's where you suck CO2 out of the air. Well, this is just as bad as carbon capture. Here's Carbon Engineering's data that they published in a paper. So for every megawatt hour of electricity, you can get 825 kilograms of CO2, according to their own data. But how do they get what electricity do they use? Well, they have natural gas turbine built into their equipment. So that takes 334 kilograms of CO2 per megawatt hour that is emitted. 334 is emitted. So the difference, the amount returned to the air, is 334. Oh, okay. 334 is from the upstream of mining the natural gas, and the 404 is the combustion CO2 from the natural gas. So a total of about 738 is emitted back to the air. The difference is 87. 87 divided by E25 is 11%. So it's 11% capture rate over a 100-year time frame. It's 31%. If we look at the similar type of graph as before, this is compared with we're going to be comparing spending energy on capture equipment versus spending that energy on replacing coal. So on the left, we'll just look at CO2 emission changes. So if you don't do anything, if you don't have any carbon capture, then there's no change of CO2 in the air. But in the case I just described, where you add direct air capture, the blue is the reduction of CO2 due to the capture equipment. The other three colors are the increase of CO2 due to the combustion of combustion of natural gas to produce energy, the upstream mining, the methane from the upstream mining of CO2, and the upstream non-methane CO2 equivalent emissions is the purple. Then if you use wind energy in the third case to run the capture equipment, all you have is the decrease. But again, if you use wind energy just to replace coal, you get a much greater decrease than using wind energy to run capture equipment. On the right is the social cost. On the right is the social cost of coal when you don't do anything. So the brown is air pollution, and the black is the CO2 equivalent emissions of the coal. And we're looking at just having the carbon capture equipment versus not. The second bar is when you use natural gas to run the carbon capture equipment. The blue is the cost of the the direct air capture equipment, that is. Blue is the cost of the direct air capture equipment. The brown is the increase in air pollution over and above that of the coal. And the black is the slight reduction of CO2 equivalent emissions. But you can see using the social cost is much higher than doing nothing when you use natural gas to run carbon capture equipment or to run direct air capture equipment. If you use wind to run the direct air capture equipment, then again, you have a carbon capture equipment cost, which is the blue. The brown, you still have air pollution from the coal that is not being reduced. And the black is the CO2 emissions that hasn't been eliminated from the coal. And finally, the wind-only cases where you use wind to replace the coal, you only have a cost of the wind energy, which is the blue, and you eliminate the air pollution from the coal and the CO2 from the coal. So if you compare the social cost, you have a six times higher social cost of using wind to run direct air capture equipment than just using wind to replace coal, and an 8 times higher social cost of using natural gas to run direct air capture than to use wind to replace coal. So just to summarize direct air capture, well, it's an opportunity cost. So because if we want to prevent CO2, well, if we want to take CO2 out of the air, if we prevent CO2 from getting in the air, that has the exact same effect as taking it out of the air. There's no difference in the amount of CO2. So we really want to focus on preventing new CO2 from getting in the air, and that is actually much more efficient. The social cost of direct air capture powered by fossil fuels is 8 times that of using renewables to replace fossils. And the social cost of direct air capture powered by renewables is 6 times that of using renewables to replace fossils. So when renewables replace fossils, however, they not only eliminate CO2, but they also reduce non-CO2 air pollutants from fossils, upstream fuel mining and pollution, pipeline, refinery, gas station, other fossil infrastructure, oil spills, oil fires, gas leaks, gas explosions, and international conflicts over energy. So we really want to eliminate those fossil fuels. using carbon capture or direct air capture does none of this. It just increases the fossil fuel industry's presence and land use and devastation, and increases air pollution, killing more people, and just taxing everybody for the higher energy cost due to the carbon capture equipment. So to conclude, carbon capture and storage and use and direct air capture and blue hydrogen are all opportunity costs that increase air pollution, mining, infrastructure, carbon dioxide, and social costs relative to spending the same money on replacing fossil fuels with renewables. Any government support for CCSU or direct air capture and blue hydrogen is a fossil fuel subsidy that will keep the fossil fuel industry in business. Any non-subsidized cost of these technologies will be paid by ratepayers. This is a tax on ratepayers. And finally, if you want more information, there's a paper on carbon capture and direct air capture and also the paper on blue hydrogen. So everything I talked about is in these two papers. And thank you very much. Hope to answer any questions you have.
Well, thank you, Mark. Thank you, June. Thank you, Albert. Ann and I are going to be going through the Q&A that exists as it is at the moment, and try to answer as many questions as we can yet this evening. I do want to say that everybody here is going to be receiving a copy of the recording, and you'll all have that as soon as we have it up and running. And with everyone's of our presenters' permission, we'll also send you slides. So June has shared hers before, and Albert, you have as well. So if you're willing to do that as well, Mark, that would be great. So if we have a few minutes here, I don't know that we'll go necessarily in the order the questions have been received, and probably want to combine a few of these together. So there was a question that I think kind of, Mark, since you spoke last, maybe this one is for you as it relates to talking about the oh dear, I just lost it. Irene's question. Here we go. Talking about the land area required. There's folks in Virginia that are terribly upset about what they see as solar taking over, and thinking about the land that's required for that land use, without also thinking about some of what you conveyed tonight. And we're experiencing that in Illinois as well. So that might be a good place to start.
Well, you reduce land use requirements when you go to wind and water and solar substantially. And first of all, you can there's so many rooftops and parking lots you can put solar on that if you're worried about using farmland, then that's a big option. France, in fact, last week just passed a law that it's going to put basically 10 nuclear reactors worth of solar on parking lots that have 80 spots or more. And they've calculated they can put up to 11 gigawatts of solar. That's huge. I can power an entire state, small state. And so, yeah, I mean, when you talk about land use, it's really a comparison. Do you want to use your land for 50,000 new oil and gas wells every year on United States property? I mean, this is what's going on, and all these millions of miles of pipeline that take up this land, or solar. I mean, you can, or why would we put a biofuel crop on land when photosynthesis is 1% efficient, but a solar panel is 20% efficient? I mean, you can get the same energy out of solar electricity by using 1/20th the land as crops are used for biofuels. This is another issue. I know in Illinois, it's a pretty big issue for, farmers are actually getting smart about this and assigning a portion of their land for solar, where they can get so much more money out of it than for biofuel crops. So I would say that it's, sure, we want to manage the land use, but in terms of solar, there's so much land. We don't need land at all for a huge amount of solar, because you can put canopies over parking lots. You have rooftops you can put solar on. You have big box stores. You have big solar fields. when you fly over a city, what do we see? We don't see solar on these roofs. Why not? That's the question we should be asking. We should be covering our rooftops and our parking lots and our schools and big box stores, everything with solar. And then you don't have to worry about using new land for that.
Thank you. And is that referenced in the slide that you have with the references with the two papers? This individual is looking for a reference to take back to her state.
Well, I'll send you a link. Yeah, I'll put some links in the chats that you can.
Okay, and we'll copy them from there. Okay.
Okay.
Okay, so you'll get that, Irene. Okay, Ann.
Thanks, Pam. We had several questions from folks asking how they can advocate against these federal subsidies of CCS. And a question, will the presenters make their case against the folly of CO2 at the federal government? And other people asking, how can they advocate against the use of CCS?
Who wants to take that?
Well, I can give you my response, which is pretty much what I said, which is that we have to, first of all, we have to use terminology that the average person understands, including the average, legislator who's not a scientist. And that gets a little tricky, but we need to basically take over control of the vocabulary. And we need to change the conversation so that we're talking on our terms. Does this stuff work? And, besides providing the data, we need to provide some examples of how it doesn't work. And we need to, I think the most important thing is to change the vocabulary, because they've controlled the vocabulary and we need to take it into our, realm and use the terminology that makes sense in the real world and makes sense thermodynamically and biophysically, but you wouldn't use those words. So we need to develop a new vocabulary in order to talk about this so that the average person can really understand what's going on.
Anybody have anything else to add to that?
Well, I think in the case of the subsidies that are going to go into the plant, the carbon capture facility in Illinois, it's my plan to work with the local representatives and try to convince them that there's things that they can do in terms of permitting to make sure that the environmental regulations are enforced fully, because in some cases the momentum is going to be so large that they're going to steamroll unless you very cleverly do things like liability. I think Mark mentioned about, and also June, that there's no such thing as safe storage. Well, right now, I know that businesses are talking about how to handle the liability. And if we can convince our representatives to have these companies post bond, so that when somebody goes bankrupt or when they go away, that they're still responsible for cleaning up. There are a number of small little steps that you can take that can have a large effect on slowing down the progress while you're educating them.
Thank you. So if we'll move on to another question, there's a question I think that emanates from a presentation some of us saw earlier today. So if we all agree we need to reduce CO2 emissions quickly and significantly, is it possible to ramp up renewable energy quickly enough so we can continue to eliminate coal-fired power plants, thereby eliminating the need for CCS, and still provide an adequate energy supply? And I'd like to tie that one in with a couple other questions that relate to baseload. What do we do with the renewables that that, yeah, and that don't necessarily provide power 24/7 every day. So maybe those two things quickly. Can we do it quickly enough? And what do we do about baseload?
Yeah, I'll try to answer. Well, first, we need to solve 80% of the problem by 2030, so we don't have time to waste. And these carbon capture projects and or building pipelines as well, they take many, many years. You know, putting up wind and solar, you can put rooftop solar in 6 months. You can get it permitted and put it up on a residential roof in 6 months in many places. But, you know, even on utility scale, it's like 1 to 3 years. Wind farms, onshore wind farms are 1 to 3 years. So we can do that rapidly. A carbon capture project, it's going to take, you know, anywhere from 3, 4, 5, 6, 7 years. And pipelines, who knows how long you need permits. So that's just wasting time too, to distract ourselves. We need to focus on things that work and things that we can deploy quickly. And these are clean, renewable energy projects and they're low cost. About intermittency, there are many solutions to intermittency. It's not rocket science. It's just an optimization problem. We combine, in fact, I just put in the links, these plans for all 50 US states, and we demonstrated how you can solve the intermittency problems with just wind, water, solar storage, and demand response. So the ways you do it are, well, there's storage. I mean, you can have battery storage, pumped hydroelectric storage, hydroelectric dams or storage. So places, you may not know, but I mean, South Dakota already supplies 125% or 120% of its consumed electricity with just wind, water, solar. And it's about 77% wind, and of the 120%, 77% wind, and the rest is hydro. Now, that also produces fossil fuels, which it exports. But the point is, it has a lot of wind, there's a lot of hydro. When you have hydro, you can use it as backup to fill in the gaps. Washington State's at around 98% wind, water, solar. It's mostly hydro. They can back up with hydro. Idaho can back up with hydro. Every state has some hydro, so that's one backup. Batteries, pumped hydro. But then connecting geographically dispersed wind, you know, the wind's not blowing in one place, it's blowing somewhere else. By interconnecting the grid, the wind turbines over the grid, you smoothen out the overall supply. Same with wind and solar. When you combine wind and solar, they're very complementary in nature. Demand response, that's when utilities give people incentives to use electricity at non-peak times of the day. Like where I am, cheapest electricity is between 11 p.m. and 7 a.m. That's when I charge my electric car, because the utility is actually charges 5 times higher at the peak times of the day than the non-peak time. That's a good incentive for people to shift the time of their electricity use. So using demand response, storage, and also over generation, we can generate more wind and solar than we need. And that really helps when we have times of high demand to actually have electricity when we need it. So anyway, I've given you some methods, but in this paper that I linked to, they basically show how we can match power demand with supply every 30 seconds for several years with just wind, water, solar everywhere in the US. It's just an optimization problem.
Thank you, Mark. Does anybody want to add to that? Anne?
Thanks, Pam. And we do have 2 folks with their hands up. Pam, I don't know if it would be best if they maybe type it in the Q&A section if possible. And then we did have a few questions about the life cycle analysis. The studies did not take into account the amount of CO2 generated in the manufacture of equipment used for the capture, pipelines, pumping stations. How much different would the results be in a complete life cycle view? And there was a few other questions as well. Just how do you capture the life cycle cost of carbon?
Well, I mean, there's so many assumptions in any of these analyses that look at what happens to CO2. And I mean, you need to build a factory. If you're going to use CO2 is used either for, it's 3 things happen with it. It's either put in the ground, which is hardly at all, enhanced oil recovery, which is 75%. And the other thing they're trying to use it for is to produce fuels to replace liquid gasoline, for example. But why would we want to do that? Because we're still burning that fuel and creating air pollution, killing people. It just makes no sense. There's no application of CO2 that's actually useful. I mean, there's soda water, but that, you already have plenty of CO2 for that. But there, so all these applications are designed to increase pollution. And so why do we even want to go down that road? They're designed, you need pipelines for this to cross land, but why do we need that when there's no point in having there's no point in continuing with these fossil fuel plants. We can see there are 10 countries in the world that are 100% renewables. There are several states that are over 90% renewables. And it's just the renewables are growing. There are 25% of all electricity in the US is now renewable. And so it's growing rapidly every year. So we should focus on continuing that path and not like looking at these options that just make no sense just from a mile away. So I don't even, you can't even do a CO2 analysis unless you know exactly what's happening to the CO2, and there's really no concrete plans for such an analysis. And then then it all depends on the assumptions you make about the leakage rates of the upstreams and the capture efficiencies, and they all, they want to claim they're 95%. And that's just, there's no actual there's no actual place anywhere that has such capture rates.
Yeah, I would just add that the life cycle analysis is something that really leaped out when I was reading the 200 or so papers that I read for the study that I did that was published in 2020. And only a very small number of papers attempt to do a full life cycle analysis from what they call cradle to grave. When you source the coal or the meth or the natural gas and through the EOR cycle. They just don't do a full life cycle analysis in most of these papers, and that's quite intentional, I think, because they don't want to include the whole thing. So it's extremely hard to find papers on carbon capture, CCS or DAC that do a full life cycle analysis. It's extremely hard to find those. They just don't do it, and I think for obvious reasons.
Well, maybe we should ask our legislators to demand that if they're going to build a capital project.
Mm-hmm.
Also, we need to keep in mind that in many cases, there's a political reason why this money is being funneled and why it's being offered. It's to keep coal companies alive. I mean, there's a recent article in which we saw what West Virginia's role was in the new IRA Act and the special deals that were made to give priority to permitting for fossil fuels as compared to renewables.
Thank you, all of you for that answer. Thank you a whole lot. And I'm going to change things up a bit, and maybe we have time only for a few more questions. So if you have a burning question, make sure you put it into the Q&A box. But I want to go back to something that June that you said. And first of all, we have Albert on the call, who's already taking over the conversation by changing the way we think about things by equating direct air capture with trees, right? So pulling that together with another question from another attendee. What do you think? How much is there a quantifiable way to look at how much biological sequestration, in particular, this person was asking about forests? What do we really need to do to make a difference to pull that carbon out of the atmosphere? Is that something that's quantifiable?
It is quantifiable, and if I had had time, I could have showed you my graphs on. There's my slides on that. I and my colleagues did a study looking at the data for the United States, not globally, just the United States. And the data show, these are data from the Department of Energy, EPA mainly, and various sources, National Academy of Sciences. And the data show that it would take less land to, for 1 gigaton removal of CO2 would take less land for biological methods than for direct air capture, if the direct air capture is not fossil fuel powered, but rather is solar powered, because solar power takes so much land. And then there's the pipelines. So basically the data, if you look at the data, it shows the advantages of biological methods, both in terms of effectiveness, they actually do remove CO2 from the atmosphere, in terms of efficiency, because they use less land and they use less water, and in terms of the impact, because the impact of biological methods is by and large positive, and the impact of the mechanical technological methods is by and large negative. So on all those 3 factors, the data show that the biological methods are superior: effectiveness, efficiency, and impact, biophysical impact.
Thank you. And maybe we need to call you back to present that information, because I don't think there's enough discussion about that potential. So thank you for that answer. Now, okay, Anna, if you take one more and I take one more, then maybe we should consider calling an evening. Maybe go for another 10 minutes, maybe.
Sounds good. I think for Dr. Carvallis, we had 2 kind of related questions. What is cannibalizing energy, and what did you mean by different drivers with different motivations?
I'll take the second one first because I understand the question. What happens in the plant, if you choose to take a plant and use its steam, the way that this is set up is to avoid the issue that Mark talked about of 30% of the plant's energy going to the capture unit. What they are planning to do to eliminate that is to have investors buy the capture unit. They will buy energy on the grid. They're just off the grid. So, and their answer is very clever on their part, because they'll say, well, we don't know if this energy came from solar or wind or anywhere. So they buy it. Now, once they bought it, that's not enough to run a carbon capture chemistry. They have to get steam from the main plant. And so what you're doing now is you're balancing steam, which is what a coal plant really generates to generate electricity. You're sharing that you're also sharing controls, because the problem that's caused always has been the eternal problem with these capture systems is, as the power in the plant goes up and down on demand, what happens is the carbon dioxide changes in concentration in the gases. And so you can't design a chemistry for something for a fixed point. So you have to balance the chemistry. You have to change the carbon chemistry. So you're connected, 2 vehicles are connected, but you have 2 drivers. And now one of the drivers has got pure motivation for pure finances. That's driving how they're going to set up their system and to capture use the chemistry. Another one has a different motivation to generate power and their issues. So when you start to have 2 control systems interconnected with different motivations and drivers, you're going to have what they call control issues, balancing issues between the 2. So that's the answer to the second question. The first question about cannibalism, I'm not sure I understand that. Could you repeat that?
I use the term.
Oh, okay.
I borrowed the term from Richard Heinberg, who's an energy expert and prolific writer. And I used it because I think it's memorable, and as long as you explain what it means, and I explained it too fast. But it's what basically Albert and Mark were just talking about. Basically, it means that, like on a power plant, the CCS cannibalizes the energy because the power plant produces X amount of energy. and you you tack the CCS equipment onto it, and the CCS equipment takes energy to run it. So if the power plant puts out X amount of energy, a portion of that has to go to the CCS equipment. So you get less energy, you get X minus the CCS use, that's put out of the power plant. So it uses some of the power coming out of the power plant. So you have less power coming out of that power plant to go to customers, which means it costs more to the customers. And also, as Albert pointed out, what often happens, and I think Mark did, is that they have to build a second power plant just to run the CCS equipment. So you've got the power plant to supply the energy to the customers, and then you've got another power plant to run the CCS equipment. And, and that's the situation you have. And then, the irony too that's going on is that this DAC plant in Texas that Occidental is trying to build, that facility, they're going to be using methane, natural gas to power the DAC equipment, the direct air capture equipment. And then they say, well, they're going to build a CCS facility to capture the carbon dioxide coming out of the CCS operation for the methane to run the DAC facility. Did you follow all that? I mean, it is a Rube Goldberg contraption that is just about beyond belief, but they say this with a straight face and nobody questions it.
So, and the way the government's dealt with that is they raised the amount of money they're going to give them for the alleged captured carbon to cover that cannibalizing cost, or buying it on the grid. So this is an incredible coordination between the Department of Energy Office of Fossil Energy and the coal community.
Thank you. If it's okay, maybe I'd like to do two questions. One, they're on different topics. And before I bring up one of those two, I just want to acknowledge the fact that in the chat, there are some discussion about environmental justice. And I don't think we've really talked about that part as the impacts on people from a justice point of view, but just to acknowledge here that everything we've worked so hard for in Illinois, but even across, with the Climate and Equitable Jobs Act, the CCS really, I think in many of our points of view, really is counter to all that we've tried to do by bringing, by leading with equity and shutting down the polluting fossil plants that are health harming in many disadvantaged communities. So I just want to lift that up before we go, because we haven't really talked about that. And we can lead strong with renewables, and we can lead strong with biological sequestration, I think. But we here in the Midwest, and all of you on this call know this, but are besieged with pipelines and carbon capture associated with ethanol plants. What do we do about this giant ethanol industry and trying to persuade folks that perhaps this is not the best use of our resources? Pipelines and ethanol.
Well,
Okay.
It's all a question of educating the public and policymakers about the facts of this case. Because it's horrible. All these technologies that are having no benefit whatsoever to society, that continue combustion. Anything that continues combustion is bad. We need to electrify everything, provide the electricity with clean renewable energy. It's simple as that. And anything that it continues to involve combustion, be it biofuels, be it coal with carbon capture, gas with carbon capture, blue hydrogen. These are just gimmicks that are just not doing anything but hurting society and making it difficult to solve our problems.
We have to educate our government officials.
I would just add that.
And make it a policy, make it an election issue.
Yeah, absolutely.
Make them know that it's important to us.
I would just add that the work that's being done by some of the people who I believe are on this call in the Midwest is astonishing. And I don't want to call out names in particular because there's so many people doing marvelous things and some recent demonstrations that are, I think, making a difference. And those people are working night and day, I know, because I meet with them every week on this, and they are having some success, and there's a lot of pushback going on. So I want to really applaud those people who are out in the field right now doing all this work, because they are doing marvelous work. And I would just say too, on the environmental justice EJ issue, I didn't use the term, but when I talk about people and places, that's sort of another way of, saying the EJ problem without using that particular term. And I think that we need to really, I would have liked to have found a way to do a study and get some and publish it on the harms from the toxic chemicals that are used in these processes, because that's going to be another disaster. Just like the pipeline rupture in Mississippi was a disaster, we're going to see chemical disasters if this stuff does get to scale, because the chemicals have to be manufactured and transported and then used and then sometimes disposed of after they're not fully used. So you're talking about a huge chemical problem that's going to be hitting the frontline and fence line communities, just as the pipelines are.
Absolutely.
Thank you, June. So, Anne, I was thinking one more question, maybe Jan's question on the small nuclear reactors. That would be a different topic.
Sure. I'm not finding it.
Towards the bottom.
Okay. So Jan had asked about small modular nuclear reactors are licensed by the NRC, but their application for a license does not even ask about the waste from the reactor. Thus, the whole cycle is subsumed in favor of the good news, and the bad news is not even mentioned.
Well, small modular reactors are a whole nother problem. They're not even proposed to be ready by till 2030. They're just called vaporware. They don't exist. And so, but they're going to have the same problem as large reactors. They're going to cost more. They're going to have they're going to have more weapons proliferation problems. They're going to have waste issues. There was a study showing that the radioactive material in the metal itself around the reactors are going to be larger due to the higher surface area to volume ratio of the reactors. These things are just, it's another gimmick. We need to, again, focus on things that work.
Another false solution.
Yep.
So I think if there are questions here in the chat there are several people who've offered resources, so we'll make that available to folks as well. And if there's something we've really missed, we'll be sure to somehow find a way to address it to the group as well as we send out both slides and the presentation. So with that, Lan, you have some closing words for us?
I do. On behalf of the Coalition to Stop CO2 Pipelines, I want to thank everyone for joining us this evening. And a special thank you to our guests, June Sakura, Albert Carvelis, and Mark Jacobson, for their willingness to share their time and insights. So you were very generous with your time tonight. Obviously, there's lots of interest in this issue and so many things that people are thinking about, and we have to work together to, work against these maybe false solutions or false starts. This webinar has been recorded, and as Pam said, we'll make it as available. Should also be posted on the Coalition website, which is noillinoisco2pipelines.org. And anybody who's registered will also get a link. So if you have any additional questions, feel free to contact us at any time. Go to our website. We're for regular updates. Finally, I know that our audience tonight consisted of some newcomers to the topic of carbon capture and storage, as well as many folks who already have developed an opinion about the technology. Whatever your thoughts are on carbon capture and storage, we hope that you found tonight's webinar to be helpful, to be thought-provoking. Even as serious questions remain about CCS, the federal government is going all in on its implementation, using the fossil fuel industry and US tax dollars to compensate those building out this massive infrastructure. And we as community leaders, as stakeholders, concerned citizens need to make our voices heard as this policy decision begins to unfold. For decades, we've known about climate change, yet we've faced it with denial, delay, self-deception, hope that technology will come to the rescue. Is CCS the key to addressing a warming climate? Do we understand the potential long-term impacts and risks? Or are we betting too heavily on a path that is diverting critical resources we need right now to build out a renewable energy economy? We hope that this webinar has helped answer some of those questions. Finally, if we're going to meet the challenge of climate crisis, we need to move quickly and effectively, and we no longer have the luxury of wasting time and money following faults or inefficient pathways compromised by special interests. The more informed we are, the better decisions we'll make, and the greater will be our chances of success. So thank you all for being here tonight. And with that, I wish you all well. Bid you good night.